Good day, everyone. My name is Mariel Nicole Anor, and together with my thesis advisor, Dr. Katia de Castro Cruz, I'm here to present my thesis entitled Mechanism Study of Beta-keto ester reduction using sodium borohydride in methanol solvent via density functional theory. Beta-keto ester is an organic compound that has a ketone attached to the beta carbon of an ester. Its structure contains two nucleophilic carbons, the carbonyl carbon here in ester and the carbonyl carbon here in ketone, which can react selectively under suitable conditions. So the reduction of beta-keto ester produces 1,3-diol, and this 1,3-diol has recently emerged as versatile building blocks in various synthetic applications. It is widely used as precursor and intermediates in the synthesis of active pharmaceutical ingredients, polymer synthesis, and inorganic transformation. So among the reducing agents which have been developed for the reduction of carbonyl groups, sodium borohydride and lithium aluminum hydride are the commonly used reagent. So this lithium aluminum hydride is a strong reducing agent capable of reducing practically all organic functional groups, whereas sodium borohydride is a mild reducing agent primarily used for the reduction of aldehydes and ketones. However, the reduction of carbonyl groups with lithium aluminum hydrides has many limitations. So it requires harsh conditions for the reduction that keeps the process low efficiency, and quite often it proceeds with great difficulty. So to develop innovative processes that allow chemical reaction to be performed under suitable and mild condition with high efficiency, we investigate the reduction of carbonyl groups using sodium borohydride. So this sodium borohydride is a crystalline salt-like compound consisting of sodium cation and borohydride anion. So the simplicity of use, cheaper cost, and in mild condition are some of the distinct features that make sodium borohydride a highly attractive reducing agent for the reduction of a carbonyl group. So in 2010, Jurong et al. Reported a detailed investigation of the reduction of various keto ester using sodium borohydride in methanol solvent. They verified that the amount of sodium borohydride necessary for the reduction to proceed is 3 molar, and it was necessary to increase the concentration of the reaction solution. However, they did not study the mechanism of reduction. So in the recent years, many experimental and theoretical types of research have been done for the formation of diols, and reduction of keto ester is one of them. Unfortunately, there have been few reports on the reduction of beta-keto ester using sodium borohydride and methanol, and there is no mechanistic detail available in this matter. That's why this study will provide a mechanism to explain the reduction of beta-keto ester using sodium borohydride in methanol solvent. The present study was undertaken to provide the whole reduction mechanism of beta-keto ester using sodium borohydride in methanol solvent via density functional theory, to determine the effect of using water as an alternative solvent, and to investigate the effect of substituents on the reduction of beta-keto ester. So the proposed mechanism for the reduction of the beta-keto ester using sodium borohydride in methanol solvent is shown in the figure. So it involves 5 sequential steps. For the first step, we have nucleophilic addition to ketone group here, and then another nucleophilic addition to ester group. Then it will undergo loss of methoxy group here. Then another nucleophilic addition of borohydride in aldehyde group. Then it will undergo 2 methanolysis to obtain the final reduced product, dipole. So for the methodology, the whole reduction mechanism of beta-keto ester was studied by optimizing the geometries and energies of all the intermediates and transition state structures using density functional theory. So all DFT calculation in this study were performed using Spartan student edition version 8. So for the first step, we have to build the molecular structure. So then the geometry optimizations were carried out to determine the low energy conformation of a molecule by minimizing the value of energy and changing the structure variables such as the band lengths and the band angles. Then we have to draw the curved arrows to indicate the band formation and breaking. Then now we have the final structure for the transition state. So for step number 5, the transition state dialog from the build menu was used to have a guess as to what the transition state looks like. If an exact match is unavailable in the database, it will attempt to provide a structure as close as much as possible, or else there is probably an error in the placement of arrows. For step number 6, the calculation setup. The calculation dialog from the setup menu will be used to specify the tasks to be accomplished, the theoretical model to be employed, and the functionals or the basis sets to be supplied. So in this case, we employ Becker's 3-parameter Liang-Por or the B3LYP functional and the 631G as series as the basis set. So for the final step, the output, then we can now have the energy. And from that, we can now have the activation energies, this one, for each step from the reactant up to the product in the reduction of beta-keto ester using sodium borohydride in methanol solvent. So let's now move on to the results and discussion. Since we calculated the activation energies of each step in the sodium borohydride in methanol system, we can now have the energy profile for the beta-keto ester reduction. So as we can see in the figure, the energy barrier to ketone reduction is computed to be 25.88 kilocalorie per mole, whereas for ester it is 51.01 kilocalorie per mole. This result shows that the ester is more difficult to reduce than ketone. Therefore, considering the higher activation energy in TS2, it is important to take note that this step wherein the six-membered cyclic intermediate is formed is the rate determining step. The quantitative information concerning the formation and breaking of bond in the transition state and intermediate can be acquired from the band length. So the bond length of BH in transition state is noticeably longer than that in intermediate. And this confirms the breaking of the BH bond. Moreover, the bond length of CO, which begins at 1.331 in the reactant complex, elongates to 1.421 in the transition state. And an increase in distance between the CO bond indicates that the CO bond has been converted to CO bond. On the other hand, a reverse trend was observed in the shortening of the CH bond from 1.619 to 1.238, and a decrease in the distance between CH bond indicates that the CH bond has been completely formed. So when the reaction mechanism was identified for the reduction of beta-keto ester, we investigate the effect of using water as an alternative solvent. So as shown in the figure, the calculated activation energies of each step in the sodium borohydride water system in the red pathway are higher than those in the sodium borohydride methanol system in the blue pathway. So the higher activation energies found for the TS1 of the TS2 can be mainly attributed to the unusual hydrogen bonds in boron hydrides, also called as dihydrogen bonding. Therefore, compared to sodium borohydride water system, the sodium borohydride in methanol system is the more effective one for the reduction of beta-keto ester. So as shown in table number 2, Juriong et al. Reported that almost all the beta-keto esters gave excellent yield except for beta-keto esters with alkyl substituents. So to counter-check the effect of the substituent on the reactivity of carbonyl carbon of beta-keto ester, we compared the energy profiles of each beta-keto esters and proposed a detailed quantitative description using density functional theory. For the aliphatic beta-keto esters with alkyl substituent, the increasing trend in the activation energy as the substituent become bulkier is evident in the figure. So as the alkyl substituent become bulkier, the steric effect increases as well. So the steric hindrance here lowers the reactivity of the carbonyl carbon in ketone, resulting in a more energy-hindered nucleophilic attack of the borohydride hydrogen. To further validate the reactivity of the carbonyl carbon, we utilize this electrostatic potential map. So it can be observed that the positive blue region here is found at the ketone group surrounding the central C atom. Thus, the central C atom of the ketone group is the most repairable electrophilic reactive site. So, the positive charge on the electrophilic C atom are calculated to be 0.843, 0.753, and 0.503 in entries 1 to 3, respectively. And based on the results, the positive charge on the C atom decreases as the substituents become bulkier. Furthermore, substituent groups can also be withdrawing or electron donating group. So in this case, for electron withdrawing, we have Cl, and for electron donating, we have O-methyl and methyl group. So as shown in the figure, the influence of the substituent is notable on the amount of energy required to form IM1 or the intermediate one. So as the Cl substituent withdraws more electron density, the C atom of the polarized CO bond becomes more positive through the inductive effect, thus making the carbonyl carbon here more reactive. As for the O-methyl and methyl group, O-methyl is more stable than methyl because O-methyl has lone pair on oxygen that are shared via resonance, whereas for methyl, it releases electron density through hyperconjugation. So therefore, the electron withdrawing increases the reactivity of carbonyl carbon, while the electron donating group decreases the reactivity of carbonyl carbon. In here, the calculated charge for electrophilic C atom increases from 0.466 to 0.811, 0.766, and 0.753. Therefore, the reactivity of the carbonyl carbon of ketone is affected by the substituents. For the conclusion, the whole reduction mechanism of beta-keto ester using sodium borohydride in methanol solvent has been investigated completely using density functional theory for the first time. The nucleophilic addition of borohydride to ester group, in which the 6-membered cyclic intermediate is formed, is the rate-determining step. Also compared with sodium borohydride with water system, sodium borohydride with methanol system is more effective and reasonable one for the reduction of beta-keto ester. Finally, it was also determined that there are several factors that could contribute to the reactivity of beta-keto ester, which are the steric effect and an inductive effect. So as for the recommendation, this study recommends using other computational tools such as Gaussian program or higher version of Spartan that can account for bigger molecule structure, as the current modeling parameter, which is the Spartan Student Edition version 8, is limited to 30 atoms only. In this way, the effect of substituents on aromatic beta-keto ester and the important role of sodium counter ion on the reduction mechanism will be further investigated.